Hello everyone, and welcome to this tutorial. We'll be doing a tutorial on the first topic of this course, which is probability distributions. So I'll briefly be talking about the concept of probability distribution. I'll mention the main probability distributions that will be covered in this class. I'll give the formula, the properties, and then we look at the application of the formula in solving some problems or calculating some probabilities of a given random variable. Okay, so the first thing that we are talking about here is the concept of probability distribution. And the question is, what is a probability distribution? And you realize that the concept of a probability distribution is quite similar to the concept of a frequency distribution that you learned in Business Statistics 1. If I may remind you, an example of a frequency distribution is a table like this. You have X there, then you have 0, 1, 2, say 3, and 4. Maybe you can put 5. Then we have a column for frequencies. So you can have values here like 4, 5, 7, let's say 6, 3, and 2. So this is an example of a frequency distribution. This is a frequency distribution. And as you know, their frequency distributions are either discrete, they are either discrete or continuous. So the example that I've just given here is a discrete frequency distribution because the frequency column, the frequency value refers to a single value or refers to a discrete value. This table here can be converted into what we are calling a probability distribution by replacing the column F with a column P for probability. So now what we need to do here is to find these probabilities. Probability that X is equal to 0. And from the basic definition of probability, we know that probability of an event A is given by number of occurrences, let's say number of times A occurs, divided by total number of possible outcomes, which you can simply call N. So N in our case is the summation of frequencies here. If you add these values here. So you take 4 plus 5 plus 7 plus 6 plus 3 plus 2. So the summation of the frequencies is 27. So that means that the probability that X is 0 will be 4 divided by 27. You can write it as a fraction or you can convert it into a decimal. So this is 4 out of 27. And using the same logic, we can say that the probability that X is equal to 1 is equal to 5 out of 27. And this will be 7 out of 27, 6 out of 27, 3 out of 27, and 2 out of 27. When you sum those probabilities, you'll get the value 1. You'll get 27 out of 27. So from this frequency distribution, we can come up with a probability distribution which looks like this. I'm going to write it in this format to save on space. So this will be 0, 1, 2, 3, 1, 5. And here we have the values. So here we have the values 4 out of 27. This is probability out of 27. 5 over 27, 7 over 27, 6 over 27, 3 over 27, and then we have 2 over 27. So this is a simple example of a probability distribution. This is a probability distribution. And as mentioned in the class notes is that probability distributions are either continuous or discrete. So we have either discrete or continuous. And a discrete probability distribution is a distribution where the value of X is a discrete variable. Like the one we have here, X is a discrete variable because it takes some specific values. So this is an example of a discrete probability distribution. Then there are cases when X takes a group of values or takes a given values in a given interval. Then those are the ones we call continuous probability distributions. So in a nutshell, what we call a probability distribution is a table like this one. It can be a graph because you can convert this information into a graphical format. So you can have values of X like this. So you can have values like this. You can have 4. So this is you can have X there. Then here you have probability. Then you can have, so this is 4 out of 27. Then 5 out of 27, like that. Then 7 out of 27. 7 out of 27. 6 out of 27. 3 out of 27. And 2 out of 27. So you can have a graph like that. So that graph and the table above, they are talking about the same thing. So again, this is a probability distribution. So a probability distribution is a table like this one. Okay, it can be a graph like this. And finally, it can be a formula. So when you talk about a probability distribution, is either a table or a graph or a formula which assigns probability values. It assigns probability values to all the possible values of X. It assigns probability values to all the possible values of X. Like this probability value is assigned to this value of X. This probability value is assigned to this value of X, and so on and so forth. The key word here is assigns probability values to all, not some, to all the values of X. And when you talk about all the possible values of X, we are referring to the sample space. We are referring to the sample space as far as the occurrence of X is concerned, as far as occurrence of X is concerned. And that's why when you sum up the probabilities, because these probabilities here will be spanning the sample space, that's why these probabilities must always sum to 1. So for a probability distribution, the sum of all the probability or the probabilities of, the probability of all the possible values of X will always be leading to 1 all the time, all the time. So that's basically what you call a probability distribution. You can think about a table like the one we have here, a graph or a formula. And then we have already mentioned that probability distributions are either discrete or continuous, depending on whether the variable is discrete or the variable is continuous. Okay. So the next thing that I want us to talk about is the examples of probability distributions. And in this class and in this course, we'll be talking about some 3 probability distributions. That is the binomial probability distribution, the Poisson is capital P all the time, the essay distribution, the Poisson distribution, and finally the normal distribution. Okay, and for convenience, we'll be focusing on probability distributions in form of formulas. So we'll not be working so much with graphs or tables. But of course, from the formula, you can always come up with a table or a graph. But the focus will be on the formula that corresponds to the binomial distribution, the formula that corresponds to the Poisson distribution, and the formula that corresponds to the normal distribution. Because that is what we'll be using to help us calculate probability of occurrence of given values of X. Okay, so let's talk about the binomial distribution. And when we talk about binomial, we have bi and then nomial. Of course, bi signifies two. Nomial means something like a name or a label, something like that. So when you talk about binomial distribution, we talk about events or variables whose occurrences are events with two possible outcomes. Events or occurrences with two possible outcomes, where one of the outcomes will be called success, the other one will be called failure. For example, when you toss a coin, there are two possible outcomes. Either you get head or you get tail. In quality control, when you inspect some products in quality control, when you inspect some product, the product will either be defective or not defective. If you are concerned with the gender of a child, so every child who is born is either of the male or the female gender. When you sit for an exam, you either pass or you fail. So those are scenarios which are binary. So basically, when you talk about binomial distribution, we are talking about scenarios which are binary. Okay, scenarios which are binary. Binary means with two possible outcomes, like the ones that I've given there. Two possible outcomes. Okay, so what are some of the properties of the binomial distribution? Because not every scenario which has two possible outcomes can be classified as binomial. So what are the properties of the binomial distribution? And there are four main properties of this distribution. The first one is that the number of trials is fixed and finite. Usually the number of trials is denoted by letter n. So n is fixed and finite. Finite means it is countable, or the number is known. The number of trials is always known. Usually we fix it in advance. Before you start the experiment, you know the number of trials that you're going to run. For example, if you're tossing a coin, you may decide to toss the coin, let's say 1,000 times. Then you record whether you are getting a head or a tail. If you are inspecting the quality of goods produced, you may decide to pick a sample of 10 items. So you decide to take a sample of 10 items, then you check out of the 10, which ones are defective, which ones are not defective. So n is always known and is fixed. Secondly, every outcome results in one of two possible outcomes. Every trial results in one of two possible outcomes. So every trial results in one of two. So that means there are only two possible outcomes. And these two possible outcomes are labeled as success and failure. One of the outcomes is called success, the other one is labeled as failure. For example, if you're inspecting the quality of goods, you can call success as the number of defective items found, and so on and so forth. Number 3 is that the probability of success, let's say the probability of the success outcome, which you usually denote by P, is constant throughout the experiment. So this probability does not change. It remains the same throughout the experiment. So we're saying that probability of success is what we're calling P. And on the other hand, probability of failure, we denoted using letter Q. And we add that, let's add it up here. There are two possible outcomes. These outcomes are mutually exclusive. These outcomes are mutually exclusive and collectively exhaustive. So this part can be better explained here. So the two outcomes, we are saying that they are mutually exclusive, meaning that they cannot simultaneously occur in the same trial. Like when you toss a coin, you cannot get a head and tail at the same time. Once you get a head, it means that the tail cannot occur or the tail has not occurred. Then we talk about collectively exhaustive. It means that if you take the probability of success plus the probability of failure, you will get the total probability, which is 1. So meaning that these two outcomes are the only possible outcomes. There isn't a third one, and one of them must always occur. One of them must always occur. The number 4 is that the trials are independent. Let's say all the trials are independent, meaning that there's no dependence of one trial, or of trials. And if you recall, the concept of independence is that if two events A and B are independent, if two events A and B are independent, then the probability of both occurring, that is, the probability of A and B occurring, is the same as probability of A multiplied by probability of B. So that is independence. Sometimes this can be written as probability of AB, like that, or probability of A intersection B. They all mean the same thing. But the idea is the probability of both occurring is given by the product of the individual probabilities. So those 4 are the conditions that must be satisfied for any given scenario to qualify to be modeled using the binomial distribution. Okay. Now, what is the formula of the binomial distribution? And we say that when the above conditions are satisfied, then this is how you find the probability of getting exactly X successes out of N trials is given by P, that X is equal to small letter x, which is equal to N combination X, P power X, Q, N minus X. So let me complete this, Elizabeth. So where X has a binomial distribution, where X has a binomial distribution with n trials and probability of success is equal to P. Okay, so that's the formula that we use for the binomial distribution. Yeah, so we're saying this is the formula that we use for, to obtain the probability of getting exactly. The key word here is exactly. That's why we're having an equal sign here. And I'm using small letter x, which is here. And then capital X is reserved for the variable itself. So X is the variable itself, is the random variable. For example, number of successes. That's what X stands for. Then this X here takes the values, the discrete values, all the way to n. So X takes the number. So the small letter X here takes the numbers 0 success, 1 success, all the way to n. N is the number of trials, so it can't go beyond there. So let me write all of them here. X is the random variable. Usually, this is the number of successes. The number of successes. Then n is the number of trials. That's why we said that n is fixed and finite. So n is always known. If n is not known, then you cannot use this formula. Or if n cannot be found out, then you cannot use this formula. Then P is the probability of success. That is P of success. Actually, this is supposed to be small letter p, yeah? So to avoid confusion. Then Q is the probability of failure. That is probability of and we know that P plus Q is always equal to 1. So if you are given P, then it is easy to find Q. All the time you'll be given P. Then it should be easy for you to find the value of Q, because it means that Q is 1 minus P. So you take away the value of P from 1, then you'll get the value of Q. Now, there is this term here. This is the combination function. So this is the combination function. Is a mathematical function which gives us the number of ways. It gives us the number of ways of choosing or getting, you can say choosing or getting X successes in n trials. The number of ways of getting X, small letter x, successes in n trials. And this value here will always be evaluated using your calculators. There's a formula, but I'll not be introducing you to that formula. So you'll be using your scientific calculator to obtain that value. And here we need to note that X is always less or equal to n all the time. The number of successes is always less or equal to the number of trials. it makes sense to say that you cannot have more successes than the number of trials. The maximum number of successes you can get is actually the number of trials. So that's why we have x less or equal to n. So I guess you know how to use the calculator to obtain this value. If you don't know, we'll be looking at it later. So basically for the binomial distribution, that is it. The properties and the formula. So before we look at application, I want us to look at the Poisson distribution. Poisson distribution. Okay. And the Poisson distribution can be looked at as a special type of the binomial, can be looked at as special, like a special version of the binomial distribution. Sometimes we can use the Poisson distribution to approximate the probabilities of a variable which follows a binomial distribution. You notice that there is a problem with this probability formula here, especially because of this part, because of that part. That part can be problematic sometimes, meaning that the formula of binomial will not be useful in such cases. And these are scenarios when n is very large. The binomial distribution becomes problematic. Okay. Because of this part only. Cannot be evaluated. Because this part here cannot be evaluated. For example, you can try, let me figure out something here. If you have 1,000 trials, let's say you want combination even 50. So if you evaluate this value here, your calculator will not be able to evaluate that part. So meaning that if you are working with a binomial distribution where the number of trials is 1,000, then it's not possible for you to evaluate this part, meaning that you can't compute that probability. So the Poisson distribution can be used in such scenarios. In scenarios where n is very large, also scenarios where p is very small. Okay, or when the probability of success is very small. Okay. In addition to this, so the Poisson distribution is preferred in cases where n is very large or infinite. You can even say unknown. So if n is very large, or it is infinite, or it is unknown, okay, that's one scenario when you can use the Poisson distribution. So in addition to that, and the probability of success, is very small. In other words, when p approaches 0, when the probability of success approaches 0, and also when n is very large, this means when n approaches infinity. These are the scenarios. These are the scenarios when the Poisson distribution is preferred. When n is very large, or when n is infinite, or when n approaches infinity, and the probability of success is very small or approaches 0. those two. When you combine these two, when you combine these properties, you'll also notice that, before I talk about that, when you talk about P being very close to 0, these are what you call rare events. Rare events. Events which are not do not occur very frequently. For example, for those who are in Kenya, the issue of earthquakes in Kenya is a very rare event. Accidents on our roads are also very rare events. Okay, if you try to compute the probability of observing an accident on a busy highway, it will be extremely small, because possibly you need to work with the number of times that accidents are observed, maybe divide by the number of times that the road was being used. I don't know how you would compute that. That is the number of times that accidents occurred plus the number of times that accident did not occur. It may not be possible actually to compute the number of times that accidents did not occur. But even if it were possible, if you were to look at the frequency of usage of the road, it would be a very high value. And if you divide the number of successes divided by the total number of trials, then it's likely to be a very small probability. It's going to be a very small probability. When you have these two, it brings forth to a third kind of property. And this is a scenario where, let's say that a combination of the above results to, especially the last part here, results to a scenario where the mean is approximately equal to the variance. The mean is approximately equal to the variance. So those are the scenarios which call for the use or for the application of the Poisson distribution. When n is very large, when p is very small, and when mean is very close to the variance. Okay, let's briefly revisit the binomial distribution. There's something that I should have mentioned up here, is that for the binomial distribution, the mean of the binomial distribution is given by n times p. Okay, and the standard deviation is given by npq. Of course, this means that variance is given by npq, like that. You can add that somewhere in your notes under binomial distribution. Okay, so if we bring the same concept, if we bring this concept down here in the context of Poisson, then we shall have, when we talk about mean being equal to variance or very close to variance, then this means that if you are working from a binomial scenario, if x is a binomial variable, we're talking about a scenario when np is equal to npq. If x is binomial. Because sometimes you may want to approximate a binomial scenario using the Poisson distribution. And when you look at that kind of expression, you realize that n times p is approximately equal to n times p times q in cases where q is approximately equal to 1. If you try to solve this equation, you can do some simple algebra, divide both sides by np. If you divide both sides by np like this, you will get that q is approximately equal to 1. And we know that p plus q is always equal to 1. Okay. And this is only true if this is true. If P is very close to 0, that's when this can be true. When this is true, then this one will be true. That will be true, because if we're saying that this guy is very close to 1, then this guy must be very close to 0. And those are the scenarios which are calling for the application of the Poisson distribution. Now, the formula that we use, so I guess we're able to pick the properties that are 3 main properties for the Poisson distribution. Then the formula that we use for the Poisson distribution is as follows. So the formula say that if X is a random variable with the Poisson distribution, or following the Poisson distribution with mean lambda, with mean given by that symbol lambda. If it was a binomial scenario, this mean is n times p, but now we are calling it lambda. Okay, so mean is equal to lambda. The probability then, the probability of observing exactly X successes is given by, so again here we're talking about an exact number of successes. So this is given by probability that capital X is equal to small letter x is equal to E minus lambda, minus power lambda, then lambda power x divided by x factorial. So that exclamation mark there is factorial symbol. It's a mathematical symbol. Okay. So where X is the random variable. For example, something like number of accidents. Things like earthquakes, etc. Then X takes the values and goes all the way to infinity. Unlike in the other case, in the case of binomial, where the small letter x was taking values from 1 to n, here n is not defined. Here n is not known. So x takes the discrete values from 0, 1, all the way to infinity. Then this guy here is the mean number of successes. Is the mean number of successes. Usually this comes as a rate. Okay, usually we'll be given this value as a rate. For example, lambda is 2 accidents per month. Okay, or 2 earthquakes per year, or maybe 1 earthquake per year, and so on and so forth. So it will always be given in terms of a rate. Sometimes we just call this is mu. It's the mean. It's the mean. It's the mean. So it's the mean number of successes. Then this guy here is a factorial symbol. The factorial symbol, which is a mathematical function. And again, I will not be introducing the formula to you, but there's a formula which helps us to find the factorial of a given number. In our case, we'll be using calculators to obtain the factorial, for example. But basically, this is the concept behind a factorial. If you're given a number x factorial, this is the same as x multiplied by x minus 1. You continue all the way to times 1. E.g., if you have 3 factorial, the same as 3 times 3 minus 1, which is 2, times 2 minus 1, which is 1. So the answer is a 6. If you have a number like, let's say 5 factorial, the same as 5 times 4 times 3 times 2 times 1. So that's the mathematics behind the factorial function. Okay. So if you take 5 factorial, this is 20, 60 times 2, this is 120. 120, etc. So you can find other values using your calculator. When you check your calculator, you will find a symbol like this. One of the keys of your calculator does this. Somewhere next to the inverse function, you will find x factorial. And then somewhere you'll also find the one for binomial, that is n CR. This is the combination. This for the binomial. You'll also find this function somewhere on your calculator. Okay, so that's basically it. That's basically it. And no, there is the E. Let me write it here. E is again a mathematical constant. Is a number. And its value can also be obtained from the calculators. If you check your calculator, you'll see that there are two E's. One E is of maybe this color, and there's another E which is approximately of this color. The one that is of this particular color here has either a box here or X. It looks like that. That is the E we're talking about. If you want to get the E, which is of color pink, I'm assuming this is color pink, you need to use the alpha. There's the alpha function on your calculator. Alpha function. And if you want to use the other E, you're going to use the shift function of your calculator. So using the alpha function might be very straightforward. You just need to press alpha, then you press the key which contains this guy. And once you do that, you will get the value of E is equal to, I don't know how many of you have done it. You will get this value is 2.718281828. Okay. If you're using the shift function, that's the second scenario here, you will also get the same answer. But as you can see, your calculator is programmed such a way that once you use the shift function and you press the key that contains this, this E, you must put the power. So you must put something here. And whatever you put here must be a 1. So you need to press E power 1. And how you press E power 1, you just press the function that contains this item, then you open brackets and you put power 1 followed by equal sign. So here you put the power by just opening brackets, you put the power, you close brackets. That's how you will end up with this. If you don't do that, you are likely to get a number which is different from this. So what you need to know at the back of your mind is that E is a mathematical constant, which is always 2.something, 2.7 something, maybe 2.718 something. You don't need to cram the value. Okay, but if you press the wrong thing, you are likely to get a different number here. Some people will get 15, others will get other numbers. So make sure you're able to do it correctly. Let me check what some of you are saying in the background, then we'll continue. Okay, so let's continue. As I mentioned earlier, is that we are now done with the Poisson distribution. It's good for you to remember the properties as well as the formula and how to obtain the factorial and how to obtain the exponent. Now, those two distributions, the ones we have discussed so far, are examples of discrete probability distributions. And that is a case where we talk about the probability of X taking an exact number or an exact value. So in those two scenarios, X will always take an exact value. And that means that X will be a discrete variable or random variable in that case. Now, there are cases when we don't talk about an exact value of X. So we talk about X taking a value within some given interval. And those are the scenarios where X is continuous. So this is a continuous probability distribution. Is a continuous probability distribution. And here, X does not take an exact value. X does not take an exact value. It takes a value within some given interval. Okay, so here, unlike in the other scenarios where we're talking about probability that X is equal to, we'll not be talking about this anymore. We can talk about probability that X is greater or equal to, which is an interval, maybe to some value here. Or we can talk about X being within some interval like this, something like that, and so on and so forth, and so on and so forth. So the normal distribution, as I mentioned earlier, is an example of a continuous probability distribution. And it also happens to be one of the most important probability distributions. It is one of the most important probability distributions. Okay, so there's a joke that I usually tell some people. I don't know that it's a good joke, but I usually tell them that when the other probability distributions grow up, they want to be the normal distribution. They want to look like the normal distribution. And we'll find that there are some scenarios where we approximate a binomial distribution using a normal distribution. There are cases when we approximate the Poisson distribution using the normal distribution, and so on and so forth, and so on and so forth. So this kind of distribution has a graph which looks like this. It has a beautiful graph which looks like this, where this is the probability curve. If you plot the probabilities, that's what you'll get. Then here, these are the values of X. And it happens that the values of X go all the way to plus and minus infinity. The values of X go all the way from minus infinity to positive infinity. In other words, X can take any value from minus infinity to positive infinity. Then it happens that the highest point of this curve here corresponds to a point here which we call mu. This is the mean. And this being the highest point of the curve, if you look at it the way you look for, if you assume this is a frequency curve, if it was not a probability curve, this will still be the highest point of the curve. And it means that this will be the mode. The most occurrent value of X be the mode. And if you look at the distribution of X from the smallest to the largest value, if you look at the distribution of X from the smallest to the largest value, you'll notice that this value is also equal to the median, because this point here is the middle point. If you look at all the possible values of X like that, then this point mu here will be the middle point. This is median. So it's the middle point. It's also the highest point of the curve. It also corresponds with the mean. It is the only distribution with that kind of property. Then you notice that the curve is symmetrical. If you have two sides of the curve A and B, where this is the line of division, you can call it like that for the time being, then side A of the curve and side B of the curve are exactly identical and are of the same size. They're exactly identical and are of the same size. Okay, So now we can figure out this as a graph. So let's consider this as a graph, and this is your x-axis, and then we have your y-axis there. You have your y-axis there. Okay, so let me give you the properties of this normal distribution, the properties of the normal distribution. And we start by making some introduction to define some symbols here. Let me do that in the background. So we're saying that if y is the ordinate, when you talk about an ordinate, we're talking about this vertical axis. Yeah? Like for example, this is an ordinate at, let's say this is value x is equal to 1. So this is the curve that we're saying y is some function of x. Y is some function of x. That is a curve. So this line here, or the height of this line here, is, for example, the value of y when x is equal to 1. That's an ordinate. Then you can have another ordinate here. Let's say this is x2, and this is f x2. So basically, that's what we're talking about. So using a formula, which we are not giving explicitly in this class, but we are saying that y is some function of x, some formula containing x as the variable. Then the normal probability curve can be plotted from an equation of this format here. You read this as y is a function of x. But in most of the textbooks, you will find that this is denoted as y is phi of x. So we use the Greek symbol phi instead of f. We use the Greek symbol phi instead of f. So phi, this guy here. Phi is just letter f from the Greek alphabet. So this statement here and this statement are exactly the same thing. It's only that they're using different symbols. Okay. So in this formula here, and remember, we are not giving the explicit definition here of the formula we're talking about, or the formula of the normal distribution. In this case here, x is a continuous random variable, is a continuous random variable defined in the interval, plus, let's start with minus infinity, in the interval minus infinity to plus infinity. So x is a variable which is defined within that interval, meaning that it can take any value within that interval. It can take whole numbers, can take decimals, can take positive numbers, can take 0, and so on and so forth. Then phi of x, or f of x, is a function of x. Is a function of x. Okay, is a function of x. That means it's some formula which has x as one of the as the variable in this case. It's some formula. When we talk about a function, we talk about something like this. For example, y is 2 plus 3x. These are a function of x. Okay, so we're saying that this y is some function of x. Okay, y is some function of x, which is completely defined by two parameters, which is completely defined. So this formula here is completely defined by some two parameters known as mu and sigma, or some people will call it sigma squared. That is the mean and standard deviation. So this formula here, the formula of the normal distribution, which we are not giving explicitly, is completely defined by some two parameters, mu and sigma, or sigma squared. If we go back to the formula of the binomial distribution, that formula is completely defined by, again, some two parameters or two items, n and p. Once you know n and p in the context of a binomial distribution, you can calculate the probability of any given value of X. In the case of the Poisson distribution, then that formula or that function is completely defined by only one parameter, that is lambda, or the mean parameter. In the case of the normal distribution, we are saying that the formula, which you have not stated, is completely defined by two parameters, mu and sigma. Okay. So now with that, we can list the properties of the normal distribution. Let's list the properties of the normal distribution. And the first property has something to do with the shape, where we say that the curve is symmetrical. It is also unimodal. And it is bell-shaped. So we're talking about the shape of this curve. We're saying this curve is symmetrical, meaning that you can divide it into two identical and equal parts. That's what we mean by symmetry. It is also unimodal, meaning that uni, meaning one. And then we have the word mode. So it has only one mode, meaning that the curve has only one peak. The highest point is only one. It has only one peak. This is the point. That's why we said that that point corresponds to the mode. It's only unimodal. Then finally, it is bell-shaped. And this is the shape we're calling a bell shape, this shape here. That's what you're calling a bell shape. So that is the shape of the normal distribution. Okay. Then we say that all the values of y, which we say that y is a function of x, we say that y is given by that, are greater than 0. So this formula here will always yield a value which is greater than 0. But it will approach 0, but approaches 0 as the value of x, approaches plus and minus infinity. As the value of x becomes extremely large or extremely small, then this formula here will be yielding values which are close to 0. As you can see from this curve here, as you move away, close to minus infinity, and you move close to positive infinity, the curve becomes closer and closer to the x-axis. Becomes closer and closer to the x-axis. And as you become closer to the x-axis, remember, these are the values of y. So this is 0, value of y, and possibly maybe these are decimal values all the way up. Somewhere up there we have a 1. So the value of y close to 0 means around this horizontal value axis. So the curve comes closer to this as you move away, closer to minus infinity and positive infinity. That's the second property. The third property is that the area between the curve, that is the area between the curve, that is this bell-shaped curve here, and the x-axis, this horizontal axis, that area is always equal to 1. Okay, so number 3, area between the curve and the x-axis is equal to 1. That area under curve is actually what we shall be calling a probability. Area under curve here is the probability. So we're saying that, in other words, we are saying, because the total area under curve is like the total probability. and we are saying that total area under curve is equal to 1, which is equal to the total probability. We know that when you sum up all the possible probabilities, you will always get 1. Okay. So sometimes you will hear me talking about area under curve when I actually imply the probability between some given points of X. For example, if you have, and I think I'll be saying that the next point, so let me just say it in the next point. Number 4, we can say that it can be shown. It can be shown that the mean is always equal to the median. And I think we try to show that. And this is also equal to the mode. That's one of the properties of the normal distribution. And the standard deviation of the normal distribution is given by this parameter, sigma. It also means that variance is sigma squared. The number 5, the 5th property, we say that the probability that X takes values between X1 and X2. The probability that X lies between X1 and X2. Hope you can see that. We're using inequalities. We are not using an equal sign. We are not talking about an exact value of X. We talk about X lying within some interval. So this is equal to the area under curve. This is equal to the area under curve. Is equal to the area under curve between the ordinates f of x1 and f of x2. Maybe if I say, usually I prefer to call it phi of x1 and phi of x2. That is between phi of x1 and phi of x2. The same story. So the area under curve between those two ordinates. We're talking about these. If this is the curve that we're talking about, and this is mu, this is of course your x-axis, then we're talking about, if you pick some values here, like let's say this is your x1 and this is your x2, this is what we are calling the ordinate at x1. This is the ordinate at x1, and this is the ordinate at x2. So the probability that the value of x lies between x1 and x2 is this area here. That is the area I'm talking about. This is the probability that x lies between x1 and x2. Sometimes it doesn't matter whether you say less or equal or strictly less. It doesn't matter whether you put this equal sign here when we're dealing with a continuous distribution. Okay. So that is property number 5. We are saying that the area under curve is actually equal to the probability under consideration. Then a very important property, number 6, we say that if you define a new variable, if we define a new variable, and usually we call it Z, and this is the definition of Z, we say that Z is equal to X minus mu over sigma. If you define a new variable Z like that, then it can be shown that, it can be shown, but we are not showing. It can be shown that, we can show that Z has the same distribution, and we're talking about this normal distribution. So Z has the same distribution, that is normal distribution, okay, as X for every pair of parameters, mu and sigma. So as long as the mu and sigma you are using here is the same one you used you used here in this formula here, as long as you're using the same mu and sigma, then X and Z have exactly the same distribution. And that's a very important property of the normal distribution. It's a very important property. It is actually with this property is when now we are going to have some formula which we shall be using to calculate normal probability values. You will notice that since the beginning, I've not given you a formula for the normal distribution. I was saying that y is some function of x, or we are saying phi of x, but I was not giving the explicit formula. Okay, if you want to know the explicit formula of the normal distribution, you can go to Google and ask the normal distribution formula. You will see how the formula looks like. But here we are going to use a simpler version, which has all the properties of the normal distribution to compute the probabilities that will be needed to compute. Now, this distribution, the one that we are defining of this variable here, so we're saying that this distribution is called the standard normal distribution. It's called the standard normal distribution. It's called the standard normal distribution. And this is now what we'll be talking about from now up to the end. Because you know that this standard normal distribution is just a special type of the normal distribution, but it's a normal distribution. Okay, it's called the standard normal distribution. And you can say that where Z, this guy here is called the Z score. We call that Z, the Z score, or the standardized value, or sometimes we call it the standardized value of X. So in other words, what we're calling Z here is just another version of X. And that's why they have exactly the same distribution. It's just a transformed value of X. That's why they have exactly the same properties. They have the same distribution. Okay. So let's note that the standard normal distribution, has all the properties, 1 to 5 above. Of course, what you'll be doing is to replace X with a Z. So where there is X, you put a Z. So this would be Z greater or equal to Z1 less or equal to Z2. So everywhere there is X, you put Z. So this remains the way it is. Area under curve. So now we'll be talking about the Z axis, not the X axis. Okay, all the way. So you replace where there is X, you put a Z. You replace the X axis with a Z axis. Okay, so it has all the properties 1 to 5 above. Additionally, and this is the additional feature, which does not contradict any of the above. Additionally, Z has mean equal to 0 and standard deviation is always equal to 1. So that is the only difference you find between the normal distribution and the standard normal distribution. But you find that this actually means that the standard normal is a special type of the normal distribution when mean is 0 and variance is 1. So if you are to draw the diagrams, you will have the same shape. You will have the same shape. If this is your x-axis, this is we're using the normal distribution. At the center here, we used to have mu. And these guys are going all the way to minus infinity plus infinity. So this is the normal distribution. Generally, if you want to use the Z, you will have exactly the same shape. You will have exactly the same shape. Forget about the apparent difference in my diagrams. But here now, instead of having mu, here you will have 0. This is the value of mu. Mu is 0, but it will go all the way to plus infinity, all the way to minus infinity. And this would be your z axis. This would be your x axis. So that's the difference between the two. The difference between the two. And you have noticed that z is just another version of x. Z is just another version of x, which is given by the formula that we stated here. This formula is very useful. That formula is very useful. Okay. So, so how do we compute probabilities of a normal distribution? So we say that consider, so now we are giving the formula, consider a normally distributed, random variable with mean, mu, and standard deviation, sigma. Then, I hope you see this. Then the probability that x, which is my random variable, I should have called it here x, that x lies within this interval, the probability that x lies within that interval, we said that this is the same as the area under curve between the ordinates at x is equal to 1 and x is equal to 2. So this can also be written in the form of z. So where there is x, you replace with a z. So z greater or equal to z1 less or equal to z2. Where z1, where z1 is equal to x1 minus mu divided by sigma, and z2 is equal to x2 minus mu over sigma. So that's how you get these values here. That's how you get these values. And even this one. So if you want to make the formula look a little bit bulky, we're talking about probability that x1 minus mu divided by sigma less or equal to z, then less or equal to x2 minus mu over sigma. The same thing. It's the same thing. So this is x1. But you can just keep it simple like this. Then you compute the values of z1 and z2 outside. So basically what we're talking about this area. Let's say this is mu. Let me just pick a value for convenience. Let me pick x1 there and x2 there. This is the area we're talking about in that scenario. We're saying that that is the same as this area here. So here we have 0, and here we have z1. Here we have a z2. We're saying that those two areas are exactly the same. If you're using the same pair, if you're using the same pair of mu and sigma, if x has a normal distribution with mean mu and this one sigma, then this would be equal to that. That would be equal to that. Now, if you were to remain on this side, for you to find the area under curve, you will use a concept that you learned in management mathematics 2, a concept known as differentiation and integration. So more specifically here, you use integration. You use integration, so you integrate the formula that we did not mention with respect to the variable, then you pick the intervals x1 and x2. Then once you integrate, you get the area under curve. I think you learned that stuff. Now, if you decide to use this method here, and this is what we should be adopting in this class, there are some tables which have been designed to help you compute the probabilities for any for a given interval or for a given value of z. Then you're able to get to read the value of probabilities from the table. So the tables are called normal distribution tables, or the standard normal distribution tables. Okay. So we shall be using standard normal distribution tables to find the area under curve, or to find the probability when you are given the relevant information. Okay. So having said that, I think now we can look at some examples. And we shall be looking at examples in binomial, in Poisson, and normal distribution. And I want us to use some questions which I've prepared, which are somewhere. We try and solve them using the appropriate distribution. Before we go there, let me know if there is any question. So for illustration purposes, let's look at these three questions, question C, question D, and question E. Then you'll be doing question F after the class as your homework. Okay, so let's answer those questions. I guess you have seen them. Question 1 or question C. So if I repeat the question says that it has been reported that Kenya Airways led in all the domestic airlines on-time arrivals for domestic flights in the year 2016. And the rate of on-time arrival is 0.75. No, 725. So this is a rate of on-time arrivals. It's like the probability of a Kenya Airways flight arriving on time. Then the question is, you are told, using the binomial distribution, what is the probability that in the next 9 flights, what's the probability that in the next 9 flights, maybe I can share the question. So we're saying that the Ministry of Transport reported that in the year 2016, Kenya Airways led all domestic airlines in on-time arrivals for domestic flights with a rate of 0.725. Using the binomial distribution, what is the probability that in the next 9 flights, 4 will be on time, all 9 will be on time, at most 2 will be on time. As mentioned earlier, if you know that you're going to work with the binomial distribution, if you assume that the random variable follows a binomial distribution, you need to answer those 2 questions. What is N and what is P? And you already told me that N is the number of flights, which is 9, and P is the probability of success, which is 0.725. And we know that P plus Q is equal to 1, meaning that the value of Q is 1 minus 0.725, which is 0.2. I mean, this is Q now, implies that Q is 0.275. So with that information, we should be able to answer any of those questions. Okay, so solution, let's answer that question. Let's answer that question. Solution. So we have to define our variable of interest, which we are calling x. So let x be the number of successes. And in this case, the number of on-time arrivals. The number of on-time arrivals. On time, I think, is the opposite of late. Okay. So we assume that we are actually taught to assume that x has a binomial distribution, or x follows a binomial distribution. Assume that x follows a binomial distribution with number of trials n being equal to 9 and p being equal to 0.725. These two are the only things you need to know when we're dealing with the binomial distribution. So now with that, now we can answer the questions. Question 1, the probability that how many flights arrive on time? 4 flights arrive on time. So we're talking about probability that x is equal to 4. That is the probability that the number of on-time arrivals is equal to 4. The number of on-time arrivals is equal to 4. So we know the formula. This is equal to n choose x, then p power x, then q n minus x. We already know that n is 9, small letter x is 4. So these are small letter x, this guy here. Then p is 0.725 and q is 0.275. Okay. Sorry about that. 0.275. So we just plug in these values into the formula and move on. So this will be equal to, from 9, you choose 4, multiply this by 0.725 power 4, multiply by 0.275 power 9 minus 4, which is 5. So you can evaluate that. If you take 9 combination 4, if you press your calculator, 9 combination 4, you should get 126. Usually you don't have to do bit by bit, but I'm just doing that for the sake of illustration. Then we have 0.725 power 4. If you press your calculator correctly, this will be 0.2763 approximately, multiplied by 0.275 power 5, which will be 0.00157. Please confirm that you are getting those values. B73. You have the option of pressing this entire item once and for all on your calculator. You just press the 9 combination 4 times 0.725 power 4 times, then you get the answer once without doing it step by step. I'm just doing this to help you confirm that you're able to press, especially this part, correctly. Okay, so evaluate that and let me know the answer that you get. So if you evaluate that, you will get this value here. We always prefer to write down the probability value to 4 decimal places. So we can say this is around approximately 0.057. 5.48. Because sometimes you may want to report it as a percentage, which would be 5.48%. So we're talking about 5.48% chance that a given flight will arrive on time. 5.48% chance that a given flight will arrive on time. Okay, so we prefer to have 4 decimal places so that in case you want to convert to percentage, then you can have the percent in 2 decimal places. Now let's look at Roman 2. And Roman 2 says the probability that all flights are on time. So it means that probably that X is equal to 9. And this will be given by 9, combination 9, times 0.725 power 9, times 0.275 power 9 minus 9, which is 0. Okay. You realize that this value here would be equal to 1. Any number combination itself is 1. Then this value here will also be equal to 1. So actually the answer is 0.725 power 9. If I were you, I would leave the answer like that. But if you want, you can still simplify it. Power 9 to get 0.0553. So that's the probability that all the 9 flights will arrive on time. I guess that is clear. Now let's look at the last one, which is Roman 3, where we are saying probability that at most 2 will be on time. At most. At most 2 means 2 or less. So the number of successes is less or equal to 2. That's what we're talking about. At most 2. When we talk about at most 2, it means that X will either be equal to 0, or X will be equal to 1, or X will be equal to 2. So those are the possible values in this scenario. Remember when we were introducing this, we said that X takes the values 0, 1, 2, all the way to N. When we say X is at most 2, it means that X is either 0 or 1 or 2. So for us to obtain that, we say that this is the same as, probability that X is equal to 0 plus probability that X is equal to 1 plus probability that X is equal to 2. So you see, this formula here was not an exact value. This was not an exact value of X. So we try and reduce it to an exact value, or to a sum of some exact values of X. So we need to find this one. So probability that X is equal to 0, it's 9 combination 0 times 0.725 power 0 times 0.275 power 9 minus 0. Then probability that X is equal to 1 will be 9 choose 1 times 0.725 power 1 times 0.725. There's a problem here. 0.275 power 9 minus 1, which is 8. Then finally, probability that X is equal to 2, which will be equal from 9, you choose 2, multiply by 0.725 power 2 times 0.275 power 9 minus 2, which is 7, is equal to that. So let's evaluate these probability values. Then from the formula up there, we just need to sum them. We just need to sum those three values, and we'll end up with probability that X is at most 2. So when you do the calculations, you will find that the probability that X is at most 2 will be given by that. You just add those individual probabilities. Maybe before we move out of this example, I will ask this question that using the information in this question, given in this question, find mu and sigma squared of the random variable X, the variable that we are describing up there. Find mu and sigma square. So you just need to recall that that mu is always given by n times p. So in our case, it would be 9 times 0.725. That is the value of mean. Then sigma square will be npq, which is 9 times 0.725 times 0.275. That means that this is variance. That means that standard deviation is the square root of variance, which is the square root of 9 times 0.725 times 0.275. So I think you can evaluate those ones later. So in case you want to find the mean and variance or mean and standard deviation, that's the way to go. Now let's go to example number 2. And the second example here is the application of the Poisson distribution. We are told that we are told to assume the number of network errors experienced in a given day on a local area network is distributed as a Poisson random variable. To assume that the errors follow the Poisson random variable or the Poisson distribution. And then you are told the mean number of errors experienced in a given day, the mean number of errors experienced in a day is 2.4. Then the question is, what is the probability that in a given day there are 0 network errors, or there is exactly 1 network error, or number 3, 2 or more errors occur in a given day? So as mentioned earlier, when you are working with the Poisson distribution, you only need to answer this question. What is the mean number of success outcomes? And you are given that answer here. The mean number of success outcomes. In our case here, success outcome is the number of network errors observed. So in our case, this is 2.4. You have to know that it is per day. It's good to note that this rate is per day. So with that, now we can answer the questions. So we start by defining our variable of interest. We say, let X be the number of successes. In this case, the number of network errors. Per day. Okay. We are told that if we are assuming that, assume X has a Poisson distribution. Assume X has a Poisson distribution with the mean number of successes with the mean number of successes, that is mu, which is lambda. You can call it mu or lambda. I prefer to call it lambda, being equal to 2.4. Network errors per day. Network errors per day. So this lambda here will come in terms of a rate. So this is errors per day, the mean number of errors per day, like that. So with that, you notice that here we are not given n. N is not known. So when n is not known, the problem might look like it's a binomial problem, but the fact that n is not known, it disqualifies it from the binomial scenario. And again, we are also told that we assume X has a Poisson distribution. So the questions are, Roman 1, probability that there are no errors, that no errors are observed in a given day. So we're talking about when X is equal to 0. Probability that there are no errors in a given day. So this, remember the formula is E raised to power minus lambda, then lambda power X divided by X factorial. And we know that X, small letter X is 0. We know that E is from a calculator, so we don't need to memorize it. But we know it's a value 2.718 something. Then we know that lambda is 2.4. We plug them in and see the solution. So this will be equal to E raised to power minus 2.4. So you don't need to write the value of E. You don't need to do that, because your calculator can give you the value of E raised to any power. Then after that, you take times 2.4 raised to power X, which is 0, divided by 0 factorial. Divided by 0 factorial. So before we evaluate this, I want you to confirm, we know that anything raised to power 0, we know that that value will always be equal to 1. So this is a 1. And if you're given 0 factorial, is always equal to 1. So you can try with your calculator to evaluate 0 factorial. So it's a 1. So this will also be a 1. So actually the answer we are looking for is E raised to power minus 2.4. And if you evaluate correctly, this will be 0.0907. So that is the answer to Roman 1. In Roman 2, the question is probability of getting exactly one network error. In other words, probability that X is equal to 1. So this will be equal to E raised to power minus 2.4 times 2.4 power X, which is 1, divided by 1 factorial. And 1 factorial is 1. So we know that you can check that from your calculator. 1 factorial is also equal to 1. So you notice that 1 factorial is the same as 0 factorial. Like that. So we just need to evaluate the numerator. So I just take the answer I got in Roman 1, I multiply by 2.4. And the answer is 0.2177. Okay, then Roman 3, probability that we observe 2 or more network errors. So we're talking about X being greater or equal to 2. Greater or equal to 2. So when we talk about X being greater or equal to 2, it means that X takes the values 2, 3, 4, all the way to infinity. It takes the values 2, 3, I just need 3 dots here, all the way to infinity. So you need to compute this probability plus this probability plus that probability all the way to the last probability. Okay. And because that is impossible, because you can't compute probabilities of x going up all the way to infinity, you use what you call the complement rule of probability, and you reverse this inequality from greater than to less than, from greater than or equal to strictly less than, but you take away that from 1. So this is 1 minus probability that x is strictly less than 2. So that's how you deal with such cases. For the Poisson, it may not be possible for you to compute this probability going up like that. So you always reverse, but you take away from 1. Now, when you talk about x being less than 2, this is strictly, remember this sign is strictly less than, and this is greater or equal. So I'm looking at a scenario where if I combine this and this, I'll get all the possible values of x from 0 all the way to positive infinity, without counting any value twice or without skipping any value. When you talk about x less than 2, it means that x takes the values 0 and 1. X less than 2 means x is either 0 or 1. So in other words, this will be the same as 1 minus probability that x is 0 plus probability that x is 1. So I sum up those two probabilities and I take away that sum from 1. I already know what is probability that x is equal to 0. And I also know the probability that x is equal to 1. So I don't need to calculate them afresh. So I just say this is 1 minus, and from Roman 1, we got this is 0.0907 plus from Roman 2, we got this is 0.2177. Okay, so when you evaluate that, you get around 0.6916. I hope that's what we're getting. Okay, so basically that is it about the Poisson distribution. I want us to look at an example on the normal distribution. The normal distribution. And before we look at the question that I showed you earlier, I want us to look at how to use the standard normal tables to find probabilities. For example, I want us to find these probabilities using normal distribution tables. Probability that Z is less than 0.01. Probability that Z is greater than minus 0.51. Probability that Z is between 0.02 and 1.02. You'll notice that the values of Z will always be rounded off to 2 decimal places. All the time, we'll be working with those kind of Z values, rounded off to 2 decimal places for convenience purposes. Okay. So I'll be sharing what we call the standard normal table. The standard normal table, it's here. So I've extracted this from a certain book. So this is the standard normal table. And this table gives us the area under the normal curve. And we are given a picture here which illustrates that the shaded part is what you're calling the area under curve. For example, this is area under curve. for values of z between 0 and some value here which you can call z1. It is the same as if I'm using x, it will be the same as this is mu, and then here you have a value x1, the area under curve between the ordinates at x is equal to mu and x is equal to x1. That's what we are talking about. Now, if you look at this table here, it's not a very long table. The first column here gives a very familiar term or item. Z is equal to x minus mu over sigma. If you revisit property number 6 of the normal distribution, we say that if you define a new variable z, which is given by that, then this new variable here will have exactly the same distribution as x for every pair of mu and sigma. For every pair of mu and sigma, then this z will have exactly the same distribution as x. That's why we are using z instead of x, and we are getting exactly, or will be getting exactly the same values. So in this column here, we have the values of z, the first column. So these are values of z from 0. And remember we said that when you are working with the z, the mean, which is equal to the median, and also the mode, is at the center. So this is the mean. So for z, the curve, the mean is at 0, like that, going all the way to plus infinity and coming all the way from minus infinity. So these are values of 0, 0.0, and we're only working with 2 decimal places. So this one shows it is 2 decimal places. For example, a z value, when z is 1.221, for example, let's say z 1.21, 1.2 is here, then 1 is here. Okay, 1.21 is that value. Later on, I'll explain what these values are all about, and so on and so forth. So 2 decimal places for the value of z. Now, the table shown here are giving the area from 0 up to a value z1 above 0. So these tables are giving the area above 0, area from 0 to a certain point on the positive side, because these are negative. If this is 0, then this is negative side, this is positive side. So the tables we are using are giving us area from 0 going up to a certain value above 0. And those are the values we are getting here. Those are the values we are getting here. For example, if you have this is 0, and then you have 1.2. We're talking about, this is the same as probability that z is greater than 0 and less than 1.2, or z is between 0 and 1.2. If you want to get that area, you will come to your tables and look for the value of z 1.2. In this case, this is 1.20, 2 decimal places, 1.20. So 1.20, this guy, 1.2 is here and 0 is here. So the shaded area here is this number here, 0.3849. .3849. That's the area between 0 and 1.2. Because of what we said about the properties of the normal distribution, we talked about symmetry. The normal distribution is symmetrical. That means that if you are talking about this area here, 0, but now here you have minus 1.20. This area here is exactly equal to, this area is exactly equal to that, the same. So this area is also 0.3849. So if you are working with values of Z, which are negative, you apply the property of symmetry. So you will work with a positive value of Z, but now you map it on the negative side. Okay. So if we can have another illustration. Now let's answer the questions that we post elsewhere. This is the question that we are trying to answer. Probability that Z is less than 0.01. So this sketch will always be very useful to avoid mistakes in whatever you're doing. So which area are we talking about in this case? 0 will always be at the center. This is a plus, is a positive value of Z, 0.01. Let's put it there for convenience. This diagram is not drawn to scale, so 0.01. We're talking about Z being less than that value. So we talk about all the values below this and all the way to minus infinity. Okay, maybe what I should have mentioned is that if this is the normal distribution and this is the center 0, then this area here is always 0.5 and the other area here is 0.5. The areas are equal. The area above and below the mean are exactly equal. When you add the two, you get 1. So this value here is obvious, so you don't need to read it from the table because you know that up to that point, that area is 0.5. What you need to get from the table is the remaining part. That's the part now that I'm highlighting in green. You only need to know this area here. Then once you get that, you add it to 0.5. So this will be 0.5, which is the lower half of the diagram, plus the area from 0, this area now. You need to read this area from your tables. The area from between Z is equal to 0 and Z is equal to 0.01. So going back to our tables, we need to locate the value of Z is 0.01. 0.01. And that value is here, 0.01. 0.0040. So that's what we add to 0.5. That's what we add to 0.5. So this would be 0.5 plus 0.004. I think it looks like that. So the answer is 0. So that's the probability that Z is less than 0.01. Okay. Some of you might think that when you talk about less than 0.01, they'll just think it's from here up to that point, and then you stop there. It means you go all the way down, all the way down. The same case applies to this, because the question is, Z is greater than minus 0.51. So we're talking about this. It's always good you have this sketch. It will help you to figure out what is being asked. Minus, so it should be below here. I'm putting it here for convenience, 0.51. And we're talking about the area above, so greater than, meaning that you take that, then you go all the way. Greater than means that you go all the way. Of course, we know the area from here all the way to positive infinity. We know that that area there, we know that this area here up there, this is 0.5. So we can say this is equal to 0.5 plus. The remaining area, the part that is shaded in green, this part here, we read that from the table. But because our tables are not showing negative values, we just assume that we are working with the area from, we assume that we are working with the area from 0 to 0.51. And we apply the property of symmetry, because this area here is exactly equal to this area here. So going to the tables, we look for 0.51. 0.51, 0.5 is here, 0.51 is there. 0.1950. Okay. So we'll take 0.5. So that is the probability that Z is greater than minus 0.51, which is 6950. Okay. Then finally, the probability that Z is between 0.02 and 1.02. So we're talking about this area. It's good for you to note whether this number is positive or negative, to know whether you are on the right-hand side of the midpoint or on the left-hand side. So these two numbers are positive. So we have 0.02 and we have 1.02. So the two values are on the positive side. So we need the area between those 2 points. We need that area there. We need that area there. Okay. And it's good for you to note that your tables will give you the area from 0 up to that point. And you'll also get the area from this point up to that point. So if you want the shaded area, definitely you will take a difference between the larger area and the smaller area. You take the larger area minus the smaller area. In that case, you'll be left with the shaded area. This is what will be happening. Huh? So you have 0, then 0.02, 1.02. So the first reading from your table will give you this. Then the second reading from your table will give you this. So you see this part has been shaded. So if you want the part that is shaded once here, you just need to take away. You take away. So probability that Z lies here, 1.02. I will start with the larger area. When Z is 1.02, when Z is 1.02, so 1.0 is here, 1.02 is here, 0.3461. And when Z is 0.02, 0.02 is this value here, 0.02. 0.0080. So you take a difference between those two. And you'll find that this is 0.3381. So as long as you have drawn this diagram correctly, and you know what your tables give you, you should be able to figure out what actually you are looking for. Okay. So maybe you can have a last example there. I think there's something I've not given here. For example, if you want to find a probability that Z is greater than 1.97. If you want to find that probability, of course, the starting point will be to do a sketch so that you can visualize the area that we're talking about. We're talking about 1.97, the area above. Okay. So you notice that your table will give you the area from here up to there. But that's not what you want. You want the area beyond there. So in that case, you will have the total area above 0, which is 0.5, minus the area between 0 and 1.97. So sometimes you'll be adding, some other times we'll be subtracting. So going back to the tables, 1.97, 1.9 is here. 97, where is 97? This value here. 0.4756. Point 0.5 minus 0.4756. And so on and so forth. You can have another one. The probability that X lies between minus 1.2, I mean Z, but it's less than 1.34. So how do you find that area? We do the sketch. Zero will always be at the center. The first value is on the lower side. So this is minus 1.2. And the other value is a positive value, which is 1.34. So we need the area in between there. We need that area. Of course, I know it is very easy for you to find this area. Because you just go to your tables and look for the area corresponding to the Z value of 1.34. So, which is equal to 1.34 here. 1.3, 1.34. 0.4099. Then you also need to add the area between 0 and minus 1.2. Using the property of symmetry, that is the same area, or that area is equal to the area from 0 to positive 1.2. So we are going to our tables and read the area corresponding to a Z value of positive 1.2. So what is that value? 1.2 is here. So in this case, it is 1.20, 0.3849. You add the two areas. Huh? You add the two areas. Zero point 3849. You add those two guys, you'll get 140 as 49. So the area is 0.7948. And I guess as you do all these, you know that probability is always a number between 0 and 1. The probability of any event is always a number between 0 and 1. So there's no way you will do some additions or some subtractions and you'll get some negative value as a probability, or you'll get some value as a value greater than 1 as some probability. That will mean that obviously your working is not correct. So that is it. Now we can go to our question. Now we can go to the question that we are trying to answer. Let's remind ourselves the question that we are trying to solve. And we are trying to solve question E. We are trying to solve question E. We are being told a set of final exam grades in a certain course is normally distributed with mean of 73 and standard deviation of 8.2. Once you know that you are dealing with the normal distribution, you only need to answer this question. And sigma, or sigma squared, is equal to what? In our case, we know that mu is 73. And know that this guy here is 8.2. So once you know that, you can answer any question, simply because we are going to use a Z value, and Z value requires only mu and sigma. Then of course, the other information will be gotten from the question itself. So let's solve the question, unless there's a question. Okay, so let's look at the example that we saw earlier. And we are told that let X be a normally distributed random variable. We are dealing with a question on the distribution of marks. So the marks scored is what we are calling X. And in this case, X is assumed to be a continuous variable with mean. The mean given there is 73. And standard deviation is 8.2. Once you get these two, you are done with the normal distribution. Those two are the only things that you need to figure out. As long as you know it's a normal distribution, that's what you need to know. Okay. So let's look at the question. And the question is the probability that someone scores what? What is the probability that a student scored below 91? So we're talking about probability that the marks scored, that is X. So here X is marks scored. The marks scored is less than 91. Okay. If you remember what we said earlier, that was some time back. We said that we can switch from X to Z in a very simple way. I want you to remember this. This is how you switch from X to Z. You can replace the value of X. You can replace the X with a Z variable, and you know how to transform it. Then once you replace X with Z, this is how you compute the value of Z. So when we say we need probability that X is less than 91, we can also say this is exactly equal to probability that Z is less than some Z1. We need to find the value of Z1. So that's how you transit from X to Z. And we say that Z1 in this case will be X minus mu divided by sigma, where X in our case is 91, this guy here. And we know that mu is 73 and sigma is 8.2. So once you plug them in, this will be 91 minus 73 divided by 8.2. So what is the value of Z that we are talking about here? We're talking about 2.195. Okay, or you can say which is approximately equal to 2.20. Because we want our Z to be 2 decimal places. So the question we are trying to answer is probability. I'm just trying to write this now without using Z1, using 2.20. Z is less than 2.20. That's the question we are trying to answer. Using our famous sketch, this is, we are looking for this. Zero is always at the center. These are positive numbers, so it will be somewhere up there. And we talk about probability that Z is less than that value. So we talk about this area below, everywhere below there. And due to the nature of the table that we are using, we know that the area from minus infinity up to this point, we know that that is 0. That is half. So we can write 0.5. Then from the tables, we look for the part that is shaded in black now. This part you get it from the tables. So you go to your tables and look for the probability or area corresponding to a Z value of 2.20. So back to the tables. Back to the tables. We look for a Z value 2.20. 2.2 is here. And 2.200 is there. So 2.20 is this number here. 0.4861. .4861. And that probability that somebody scores less than 91% will be 0.9861. It's a very high probability that someone will score less than. Of course, 91 is a very high mark. Okay. So we have just calculated the probability of a given scenario using the normal distribution. So I want us to look at Roman 2. And the question, Roman 2 is, what is the probability that the student scored between 65 and 89? So Roman 2, probability that the marks scored, which is X, is between 65 and 89. Doesn't matter whether you put less or equal like that. Doesn't matter. So we're saying this is now exactly the same as a Z1 there, less than some Z, less than some Z2. So I replace those values of 65 and 89 with Z1 and Z2. I need to get a value of Z which corresponds to X is 65, and a value of Z which corresponds to X is 89. So we know that Z1 will be equal to x1 minus mu over sigma, and your x1 in this case is 65 minus our mu is 73 divided by 8.2. So this is something you can evaluate. Then Z2 is x2, that's the other value of x, minus mu over sigma, which is 89 minus 73 divided by 8.2. So let's evaluate those values and then we plug them here. We plug them here. And using the tables again, we'll be able to get the value of Z. So these are the values of Z1 and Z2. Then this is the expression that we are trying to evaluate. Then using our famous sketch, this is what we are looking at. 0 is always at the center. This guy is negative, so 0.98. This diagram is never drawn to scale. So don't worry where I've put my minus 0.98. I know it should be very close to 0, but I want to see it clearly. Then 1.95. So I need the area between those 2 points. Need the area between those 2 points. So probability that this is minus 0.98. 1.95. I can start with the positive side. The area above 0, you go to your tables and look for the area corresponding to 1.95. Corresponding to 1.95. So Z of 1.9, 1.9 is here. Then 5 is here. 0.4744. .4744. In the area below, I'm using the property of symmetry. The area below here, using the property of symmetry, I will assume this is a positive 0.98 and read the area corresponding to 0.98. So 0.9 is here. Let me remove these lines. 0.9 is there. Then 8 is there. 0.3365. .3365. And when you add those two, you get 0.8109. And you can check whether it's correct. So the last question, where we are told, suppose that 15%, we're told that 15% of the students failed or they scored grade E. So if you are to draw the diagram, you would be talking about the lowest performers. You know, these are values of X. This is mu, this is X, and these are increasing values of X towards infinity. And then this is towards minus infinity. Of course, we know that the marks will be positive values. So this value here, so this is X-axis, no problem. This is X-axis. Is X-axis, but here we have mu. And we know the mu, we know the value of mu in this case. We know mu is 73. So this point here is 73 like that. We are told that there are people who scored very low marks here. We don't know how much they scored, so we can call this value here x1. And this area here, or the probability, is 15%, which you can write in decimal form as 0.15. So if you know the shaded area is 0.15, of course, you know this area here is that 5% or 0.35. Can even say that. So with that information, are you able to figure out the value of x1? Because this value here, this is your pass mark, or the starting point of grade E start point or cutoff. Are you able to figure that out? That's the question that we are trying to answer here. That's the question we are trying to answer here. Okay. So we can figure out a scenario where we have a Z. We know that Z is always equal to X, I'm calling it X1 minus mu over sigma. From tables, you are able to figure out the value of Z, get the value of Z corresponding to an area of 0.3500 from the center. Either from the center to a value x1 to x1. Yeah, let's put it like that. So we get that Z, which gives us a probability of 0.35. So once you go to your tables, you will not be looking inside the table and look for a value of 0.35 or very close to 0.35. We look for 0.35 or very close to 0.35. I believe if you check here, the nearest value you have is around, I think this is the nearest. So it is slightly above. Huh? It is nearer than this. It is nearer than that. So we prefer to work with this value. It's slightly more than 0.35, but it's the nearest that we have from the table. So you choose the one that is closest. This one is around 0.0015 points less. This is 0.0008 points above. So we prefer this one is closer. So basically we're talking about this. This is what we are looking for. But here we have 0.3508, and we have another point here, 0.3485. So this point is closer than this point. So we pick the one that is closest. So in our case, we settle with a Z value of 1 point. So this value here is coming from a Z value of 1.4. Sorry, 1.04. A Z value of 1.04. So that is the Z value that we'll use in our formula to help us figure out the value of X. Okay, so here we need to put 1.04 is equal to X1, which we don't know, but you know that mu is 73. And our sigma is 8.2. You see, with that, it becomes a very simple problem. With that, it becomes a very simple problem because now you can get your cutoff point as 1.04 times 8.2, which is that, then plus 73. Plus 73. Sorry, there's a problem here. The value of Z that we are getting here is below the mean. The value is below the mean. Huh? So since the value is below the mean, this value of Z will be a negative, not plus. Because the value is below the mean, it will be a minus. So that means we'll be having minus 1.04 times 8.2, which is a minus something. Huh? Then we add 73. So we'll get x1 is 64.472. This is the grade E cutoff point. Grade E cutoff. Okay, around 64.5. So I want you to notice that sometimes you may be asked something else, not the probability. Of course, when you ask the probability, that's an obvious question, so it should be easy for you. But if you are asked to find the value of X, like in this case, you just need to know that you are working the other way around. Huh? You start by getting the value of Z, and then you move on. So guys, I think that is what I intended to cover with you today. I want you to try the last question here, question F. You try question F on your own. You need to read and understand. You need to recall the properties that we listed of the different distributions, but I can give you a hint. We are told that the mean number of defective apples in a tray is, so this is mean, is 7.8. And variance, which is sigma square, is 2.73. Find the probability that there are exactly 4 defective apples. So we're looking for probability that X is equal to 4. That means that we are not talking about the normal distribution in that case. Because in the case of normal distribution, we never talk about X taking an exact value. We talk about X being in a given interval, in some range of values. So this one must be either the Poisson distribution or the binomial distribution. So using the properties of the binomial and the Poisson, you should be able to say whether this scenario here represents Poisson or binomial. A further hint is that for the Poisson, we say that mu should be approximately equal to variance. So we're saying that these two numbers here must be approximately equal. And clearly these numbers are not approximately equal. So that leaves us with the option of binomial distribution. So here we shall use binomial formula, binomial distribution, to get this. So for you to answer this question using the binomial distribution, you need two things, n, and you need p. So that is the task that you have. Find n and p in this scenario, assuming that it's a binomial scenario. So that is it, guys. I want us to stop there. Thanks for coming. I'll be answering any questions in the background. Goodbye.